Roughly how I thought we could spend our time is by firstly just looking at a little bit of a brief historical context. What actually gave rise to this whole somewhat unusual field of quantum mechanics, and then moving into what are some of the underlying ideas, again at the sort of very high level, and then how does that actually manifest itself into what I call quantum weirdness. There are no analogs at the human scale, so it really is, I guess, an exercise in mental gymnastics, if I could call it that. And then seeing how it actually manifests through this thing called, these are all the effects, but what is the underlying mechanisms or reality on which these quantum effects unfold? And the best description we have of that to date is something we call the standard model. So just a very quick look at that. And then maybe couching it all in, what are the limits of human senses? After all of our thinking is informed through stimuli that come through our senses. Does that in some sense frame and even limit what we're able to understand of the potential reality around us? And finally, coming down from the cerebral to maybe a little bit of more the applied, if time allows, we could have a quick look at some of how this ability to control these fine-grained quantum effects is now manifesting itself in terms of applications which are already finding their way into real-world applications. Well, sort of going back really to the turn of the century, at the end of the 1800s, early 1900s, it looked like, we had really understood the world around us. And, from the falling of apples on the head, in fact, this tree here on the left was a picture took at Cambridge, and it's supposed to be a descendant of the tree under which Newton stood, and the apple actually fell on his head, to the motion of stars, and more broadly to how objects move in space around us. We thought, we really sort of understood nature quite well. In fact, as a sort of capturing on a bit of a funny note, some of the hubris of the time, Lord Kelvin, right, was responsible for the Kelvin scale of temperature measurement. So we have Fahrenheit, Celsius, and Kelvin. He reckoned that there was nothing new to be discovered in physics now. And this is like end of the 1800s. All that remained, he thought, was more and more precise measurements. And then there was actually something which was apparently ascribed to the commissioner of the patents office in the US, which was something along the lines that everything that can be invented has been invented. And he was sort of quite doubtful about the future of the patents office, which he thought would shrink and eventually disappear because there was nothing more to be found. I've been told that was a bit apocryphal. It wasn't quite right, and somebody traced it back to, there's this magazine used to be there around called Punch magazine. And in 1899, there's this little piece on the left of your screen. I apologize for the quality of that. We couldn't quite get a clearer version of it. But it's a little piece there, which is the genius walking in to the office of a publisher, and there's a boy there. I won't read you through all of it, but basically the key bits there are, which I think capture the zeitgeist of the time. And the genius says, "Isn't there a clerk who can examine patents?" The boy goes, "Quite unnecessary, sir. Everything that can be invented has been invented." So I thought, quite interesting. But at just around that time, there was still a few problems that just could not be solved. And with the physics of the time, so the physics of the time, this was this so-called classical physics. And, you had people like Newton and Maxwell and others who had given us great insight into how the world, at least at the human scale, worked. But there were a few things that still couldn't be addressed. And one of them was a so-called black body radiation problem, which concerned the spectrum of radiation emitted from stars. And using the laws of classical physics, try as they might, scientists just could not come up with an explanation that would fit those laws of classical physics. So a physicist called Max Planck came up with an explanation for this after almost a decade of struggling with it. But in doing so, he had to come to a radically different thought, which was that energy, which was thought to be continuous, that you could get in whatever quantity you wanted, actually had to be produced in discrete quantities. And he termed the term quanta for that. Now, this was quite revolutionary. Even Planck himself, for a long time, was somewhat a disbeliever that he had actually come up with something that was correct. But the thing was, it just fit observations so well that it was difficult to deny it. And then, following that, you had a number of other eminent scientists. So Einstein himself, in 1905, he came up with the so-called explanation of the photoelectric effect, which was when you have electromagnetic radiation hitting materials, that you found electrons and therefore electricity would generate. But again, to get a good explanation of how that worked and how it tied in with observations that we saw of the world, he had to also similarly assume that energy was in quanta. And even though the ideas that underlie quantum mechanics are so unnatural, so that this idea of superposition, entanglement, and being in many states until observation occurred, it really sat, even with Einstein, almost through to the end of his life. He was not quite convinced of the legitimacy of, I guess, the mental foundations or the theoretical foundations of quantum mechanics. But over thousands of experiments and decades long, time and time again, every time quantum mechanics has been put to the test, it's come up, dare I say, trumps. And it's been just proven to be correct on so many different areas. And we'll look into those in a short while. So here's a little bit of a map of the domains of theoretical physics models that we've had. So it's on your x-axis, sort of going downwards, is your scale of in physical dimensions going across, and then on the y-axis is speed, and that's going up from sort of a human scale right up to the speed of light. And at scales which are much lesser, smaller than galactic scales, or even interplanetary scales, and at speed much less than the speed of light, classical mechanics. So all the things that Newton, Maxwell, and Carnot and people like that from thermodynamics have taught us, served us perfectly well and worked exceptionally well. But once you get outside of this domain, what you see is that, particularly as you get to the scale of the very small, quantum mechanics, classical mechanics just doesn't work. It doesn't explain how things work at that level. And quantum mechanics, in fact, kicks in and works particularly well. And of course, on the other side, the right-hand two columns that you see there is once we start approaching the speed of light, and we're not going to be touching on these topics today, but you move into relativistic mechanics. So these are the ideas of Einstein and other luminaries. And finally, there is this idea of quantum field theory, which is just emergent with attempts to pull together relativity and quantum mechanics. But today, we'll just limit our conversation to the bottom left-hand corner with quantum mechanics. So as we look into the field of quantum mechanics, well, what is it? So classical physics, which we just talked about, sees what we call space-time, and we see that as four-dimensional, as many of us may be quite familiar with. And Einstein had believed that the fabric of space-time was smooth and continuous, and his ideas of general relativity provided us with an excellent description of nature at visible scales, and particularly at the very large scale. But quantum mechanics actually aims to go to the other end of that spectrum, and what it tries to do is to match a theoretical framework to a very large body. And much as classical physics is a great approximation, as we said, at human scale and speed, quantum mechanics really is far more accurate once we get to atomic scale or smaller. So I think, again, perhaps No surprises here. So, what does quantum mean? So it comes from the Latin, very simply for how much. And it tries to sort of embody this idea that what we measure of matter or energy in the observable in nature is in discrete units. And even though we think of space and time as being continuous, when you get down to the smallest level, they actually have minimal values, therefore are granular, and quite at odds with our own human experience. I'm sure you would agree. So if we sort of look at quantum physics, one of the key ideas there is this thought of a quantum state, which is a mathematical model which provides us a probability distribution of the outcomes of each possible measurement, which is quite different, right? In our human scale, if we measure something, I know it's a 1 or it's a 0, or I know it's 1 meter, or I know it's 1 hour in the time dimension. But once you get down to the quantum level, this odd thing happens. And in fact, it's not even probability. There's this bizarre concept called probability amplitude, but probabilities can go negative. Now, there is no physical analog that I can offer you up that could even begin to define what a negative probability could be. But what it does provide us is a framework which very well describes some of the phenomena we see. And what it means is that when you get down to the atomic and smaller scales, there is no absolute. Things that we see, position, energy, even time, are governed by a probability distribution. So, while at the human scale, I'm here and I am not, on the chair next to me, but at the quantum level, you have some probability of being at a particular position, a lesser probability of being somewhere else, but even an infinitesimally small probability of being at the other end of the universe. Very strange idea. We don't have any parallels, so we can intuit this, we can form a mental model, but our physical experiences will provide us no help in trying to understand these phenomena. And basically what quantum mechanics says is that the knowledge of this quantum state, along with the set of rules that govern how it changes with time, can give us the knowledge of all that we can possibly know about how that system moves through time. So the quantum state and this it's actually called a set of operators in quantum mechanics that govern how that state will move through time. So as you see down here, so wave functions define the quantum state itself, and operators tell you how that quantum state changes with time. And you have an operator for each observable, which is, so it could be energy, it could be momentum, and so on. A range of different physical quantities, if you'd like to think of it that way. And when we think about quantum states, a mixture of quantum states, interestingly, becomes a quantum state itself. But a quantum state which is fundamental in some ways, in that it cannot be written as a mixture of any other states, is a so-called pure state. And whereas all other states are the so-called mixed states. Interestingly enough, what we are now seeing is, of course, we've all heard, right since our schooling, of this mass energy equivalence. And of course, Einstein's perhaps the most famous scientific equation known, E is equal to mc squared, embodies that mass energy equivalence. Recently, though, what we're starting to see is that there's a third equivalence, which is on information. So that I still actually haven't had the opportunity to read this because it's a paper that I just discovered had been released last year. Some scientists have actually quantified that if you had a storage device and you stored a terabyte of information on it, that theoretically they've calculated, and I imagine this is still being validated, that the actual mass of that device would change because of the terabyte of information stored on it. So I must say this does my head in as well, so that you can actually find that information at it, if one could get down to the most fundamental level of it, is actually equivalent to very small energy packets, which in turn is equivalent to our so-called mass that we perceive at our human scale. So we continue to see this development of this framework where we have mass and energy, but interesting enough, information and I guess knowledge also starts to become equivalent at the most fundamental levels with mass and energy. So in line with this, if you do actually try to look at the fabric of space-time at the most microscopic level, the suggestion is that you actually find it comprises teeny tiny grains of information, but at the most minute scale. So a proton, to give you a rough order of magnitude in size, so a proton in the nucleus of an atom is about 10 to the minus 15 meters in size, roughly. Which, as we all know, is extremely minute. But this scale, what we are talking about, is something called Planck scale, is 10 to the minus 35. So 100 billion times smaller than a proton. And of course, we today, with our level of scientific capability, do not have ability to measure down at those absolute fundamental scales of nature. So what are some of the tenets of quantum mechanics? Again, this is not intended in any way to make anybody really a quantum expert, but there really, to my mind, are three fundamental ideas that underlie pretty much the whole field of quantum mechanics. So the first is this idea of wave-particle duality. As we touched on in the opening, we always thought that electromagnetic waves were waves, and matter was made of physical particles. But increasingly what we're finding is that all energy and matter, for that matter, have this dual nature, where they can, in sometimes, exhibit wave-like characteristics, and at others, very much point particle type of characteristics. And this was epitomized by what you see on the right-hand side of your slides here. It was a so-called Young's experiment. So it was in the early 1900s, a scientist called Young conducted this experiment where he had a light source and he had these two slits through a partition there. So as you can see, the light source is if you look at the middle graphic there, with this light source, and there's two very tiny slits in a partition. And if you had detectors on one or both of those tiny holes just to measure the amount of light going through, you would get this kind of behavior, which is, as you'd expect, with if it was single photons of light, we get two well-defined distributions of light directly behind the holes themselves. So that sort of reflected this thought that, that light was made of photons and the single particles, and that one particle, if it would go through the left slit, it would form that pattern you see on the left-hand side. If it went through the right slit, it would form the pattern on the right-hand side. Now, the oddest thing that occurred was as soon as they removed the detectors to measure what was happening at each slit, you got what you see on the right-hand side of your slide there, which could only occur if light behaved as a wave. And this is sort of what's called wave interference. So if you had, let's say, a wave that was going out, let's say you dropped a pebble in water and you put this partition in, you had two holes in the partition, and the wave was spreading out and it made its way through the two holes. And then you looked at what the pattern looked like some distance behind those two holes, you would find that as those waves went through the two slits, you still have the wave fronts forming behind the two slits, and they would then interfere. Sometimes they would be what's called positively or constructively, and you get a bigger wave, and other times destructively, where they cancel out and you get no wave there. And you saw this pattern, which was of light, no light, light, no light, light, no light. Very strange. You could not reconcile that with the particulate nature of light, which was sort of suggested by the photonic model of light. So this really sort of captured the wave-particle duality, and even a sort of a classical concepts of waves and particles all of a sudden had to be rethought. And while this was sort of bubbling along in the 1900s, really in about the 1920s, through the work of Einstein, de Broglie, and others, Niels Bohr, you really found that quantum mechanics started to develop very much more strongly and in a more substantive way. And this was verified not only for elementary particles, but also, interestingly enough, for atoms and even molecules. So atoms, imagine that, started behaving not just as discrete bits of mass, but you found if you sent an atom through and you didn't observe what was happening through on the two ends of the slit, you'd still get this pattern of interference and non-interference. How could that happen with something that we regard, very much as something solid? So the thing is, though, why we as human beings can't reconcile that is because de Broglie came up with this formula which says that the wavelength of a particle is inversely proportional to its momentum, or let's think of it as mass. So for subatomic particles, which are very light, you can get observable wavelengths. But once you get to the size of a human being, because we are much more massive than protons or atoms, therefore, because of the inverse proportionality, the wavelength becomes absolutely tiny, down to that level, we talked about, or the information packets, 10 to the minus 35 meters. So we can't measure that at human scale. And therefore, it is something that is so foreign to our experience. And even the great Einstein found this somewhat puzzling, right? So he said, though we must, sometimes use one theory and sometimes the other, and either times we might use either of them, we've got this new difficulty. We've got like two different, contradictory pictures of reality, and neither of them fully explains what we observe, but together they do. Really, really odd. The second idea, which defines quantum mechanics, so that was about the duality, is about this quantization. We briefly touched that at the open. So that energy in microscopic scale systems is quantized. It can only have certain discrete values. And at that quantum scale, that transfer of energy can really only occur in lumps of energy. It can't be sort of any random value. It has to be quite discrete, well-defined values. I guess the analogy is like having a car that can only travel at certain speeds because its energy can only have it. So I can go at 10, 20, and 30. And the little picture on the right-hand side here, tries to capture that. So as opposed to a fireman's pole, which you can just slide down and be anywhere on the pole, it's more like being on a ladder where you can only have very specific quantizations of energy. And in fact, Max Planck, who, as we said in 1901, had come up with this explanation for black body radiation, he was awarded the 1918 Nobel for his seminal work in resolving this conundrum around black body radiation. And Einstein's in 1905 was considered his miracle year, where he just had this amazing set of insights, and he published 4 incredibly transformative papers in that year. One of them talked about the so-called photoelectric effect, which is when you have materials and you have electromagnetic radiation hitting those materials under certain circumstances, it would eject electrons. And then, so we commonly use it, in fact, in our solar panels today. So we're already leveraging these ideas. But it's interesting, it doesn't happen in all circumstances. I can't just shine any old light and the photoelectric effect will occur. It occurs under very certain, very specific frequencies. And below certain frequencies for certain materials, it just doesn't occur, which again couldn't be explained by conventional classical physics. It required this idea of quantization. And in fact, Einstein, for when he received his Nobel Prize, was not for relativity, it was for the photoelectric effect. The third idea is this thing of the uncertainty principle. So some of you may have some either happy memories or nightmares from school physics, where you had the Heisenberg uncertainty principle. And essentially what it captures is the limits to our ability to know nature, I guess, in her entirety. So I guess nature is a bit coy, and she will only tell you up to a certain amount about herself. And the Heisenberg uncertainty principle, captures that ability which limits absolute knowledge of reality, if you will. And the idea really applies to what we call related pairs of observables. They call them conjugate pairs of observables. And an observable is anything that you can measure. So here's a couple of examples of conjugate observables: energy and time, or position and momentum. And I think, this little graphic here tries to capture that. So on the left-hand side, that delta X and delta P, that's the uncertainty in position and momentum. And that the uncertainty relationship says that it'll always be greater than the H, that's called H bar there, which is so-called Planck's constant. It's a fundamental constant of the universe, as best as we can tell, an invariant number. Or the uncertainty in energy and time always has to be greater than that. So it implies that you must always you can make one variable very accurate, but that means the other one, you have a lot of uncertainty. So you can never get to a point where you know both of these variables very well, because they always, when you multiply the uncertainty in both, always has to be above a certain number. And the graphic on the right-hand side tries to capture this idea. So we want to look at an electron and try and determine its position and its momentum very accurately. But to do so, you need to have a photon to look at it. Now, and how you can measure something on each of the two graphics there, the top right-hand side is basically like a microscope, and an eye is what that's supposed to represent. So if I want to know the position accurately, I need a photon with a short wavelength, a small wavelength. But small wavelength photons have a lot of energy. So if you think about X-rays, a lot of energy. So that gives me a good precision on placing where the electron was. But because I've got high energy, now I don't really know how much energy the electron itself had. The thing on the right-hand side tries to give you the alternative picture. So I use a low energy photon, maybe like an infrared ray. Now, the wavelength is quite wide, so I don't know very well where that electron was, but maybe I know its energy or momentum much better now, because my impact on it, because infrared is low energy, it hasn't affected what I'm looking at so well. So this is the kind of trade-off that we find in nature throughout quantum physics. So that's probably the third important idea that underlies quantum mechanics. But I think if you, at some intuitive level, have an understanding of these three ideas, it really gives you a pretty good idea of what quantum physics is really all about. So this is what I call quantum weirdness. So when you get down quantum level, funny things happen. And here's four examples which I think sort of capture some of that. So this is the idea of quantum superposition. So, a couple of slides ago, we talked about quantum state. So where it's in a particular state governed by a probability distribution. But consider a system that can exist in two quantum states. For simplicity, let's just call it a 1 and a 0. And in our world, let's say if you look at a bit in a computer, it's either a 0 or it's a 1. In the quantum world, somewhat bizarrely, these states can exist in superposition, where it is a 0 and a 1 at the same time. And maybe you'll just hold this thought, because this is an idea which is being exploited in quantum computers, which is an emergent technology, and their bits are called qubits, which are 0 and 1 at the same time. So as you can see on the graphic on the right there's this skateboarder who's happily skateboarding in two directions, and he's in a superposition. But as soon as you look at it, what happens is this idea of what's called wave function collapse, and he drops into one particular position. Very, very strange. And this is, as I said, an idea that's being leveraged to great effect in our emergent class of computers called quantum computers. So the idea that you can be in two places at once or two states at once, very strange. No human scale and analog that I can offer you there. And this was sort of captured by Erwin Schrödinger, an eminent physicist in the 1920s, who was trying to illustrate how ridiculous a thought this could be. And this was the idea that you've got this hypothetical cat in a box, and in the box, you've got a nuclear source that at random will emit a particle when it decays. And the third thing in the box is a vial of poison. So when that particle decays, it emits, when the atom decays, it emits a particle which will hit the vial, open up the vial with the poison, and the cat will die. So his idea here was to try and, he was actually trying to highlight the ridiculousness of this whole idea of superposition. So he said, well, if you don't open the box, how do you know if the cat's dead or alive? You can't know. So does that mean it's dead and alive at the same time? Because you don't know when that nuclear particle would decay, as governed by the laws of quantum mechanics. And so bizarrely, even though he raised this as something to illustrate the ridiculousness of the thought, it in fact has now become almost a poster child of trying to explain superposition, and that the cat is, as best as we can tell, dead and alive at the same time. So that's superposition for you. Entanglement, another really strange idea. So what this actually talks about is that you can have two particles, and that the state of any individual particle is indeterminate, but quantum mechanics can tell you what the pair will do. So a way to visualize this is to think of a photon which has certain energy. Now, photons can split into two half-energy photons as well. So you have a photon, it's trucking along, and all of a sudden it splits into two half-energy photons, and one goes to one end of the universe, the other goes to the other end of the universe. The odd thing is that even though these might be at interstellar, intergalactic distances, if you look at one of those, you can straight away infer a corresponding property on the other one. And you can infer that property about the second photon at a speed that's greater than the speed of light, as best as we can tell. There's been thousands of experiments because people have said, no, well, this can't be right. There must be some kind of secret communication going on between these two particles that, we can't pick up on. But, according to the laws of physics, as we know, nothing can travel faster than the speed of light. And this, as best as we can tell, seems to be occurring instantaneously. In fact, Einstein was pretty concerned about this, and he referred to it as spooky action at a distance. And he spent, many of his, probably the last 2-3 decades of his life, still trying to figure out how is this occurring? Is there some hidden variable that we haven't measured, which if we knew about, we would be able to predict, but none has been found. And this entanglement, even though we don't know how it works, we still don't know, but we do know that it is a real phenomenon. Third thing is what we call the observer effect. So it sort of harks back to the superposition idea, but the thought is, and this is the only slightly scientific chart that I've put up here, which shows what's called the wave function distribution. So on the XY plane in the little graphic is where you are in space. So you can think about the position of a particle, and roughly you can think of the z-axis, the axis going upwards, as being the probability of the particle being at that position. So as you can see, it's in this case a sort of conical shape, and center of the cone represents the point of highest probability where that particular quantum state is likely to be found. But as you can see, because there's a distribution there, it could be at any one of those other places as well, but with a slightly lower probability. The odd thing is, as soon as you look at this, it collapses. And as you can see there on the right-hand side, it becomes localized to a very specific spot. So I think this sort of goes back to what some of the ideas we've been referring to throughout this talk, that this is called the collapse of the wave function. It just, as soon as you look at it, it localizes itself to a very specific discrete value, whatever it is that you're measuring, whether it's position, energy, momentum, or any observable. And the fourth idea I just want to share with you is this odd idea of quantum fluctuations. So if we think of empty space, we think, well, and then there's no light sources, no energy sources even. The weirdest thing is that when you look at it, you find that energy can spontaneously create and self-destruct as well. Empty space with nothing in it. So I sort of sometimes think of it as the crackle of empty space, if you want to visualize it that way. It's almost as if out of nothingness, energy can be borrowed, and you get negative energy created, and then you get energy come into existence at another place, and then spontaneously it self-destructs and vanishes. This somewhat disconcerting graphic on the right here tries to sort of capture that creation and destruction of energy at outer space. And interesting enough, they suggest that right at the creation of the universe, this may have been responsible for the expansion of the universe, this spontaneous creation of energy, which then got amplified and formed the seed of everything that we can observe in our universe today. So that's a sort of fourth idea, a thought that's kind of different to what we see at the human scale, but it's sort of interesting, and you have to accept it. But if you accept it, you can somewhat intuit what it's trying to convey. And more than convey, this is actually the nature of reality. This is what actually happens at the most microscopic scale. So standard model is this theory, it's the best theory we have. So far we've talked about all the effects, what measures, and that we can see. But what are the actual objects that are carrying out these effects? And that's what the standard model tries to come up with. It is the best explanation we have to date, which captures the four fundamental forces that we have in nature. So electromagnetic, the weak and strong interactions, but unfortunately it doesn't capture gravity. We still haven't got that ability to include that into this model. And it classifies all known so-called elementary particles. So that's a particle which has no substructure. It's not composed of other smaller particles. And this is what it looks like. So you have this category called fermions, which are the purple and green boxes that you see. So the left three columns there. And essentially everything that we see as matter is composed of those purple and green subatomic or elementary particles. The ones in the orange there, so the gluon and photon and bosons, these are what we call force carriers. So they give rise to those forces that we looked at, the weak and strong nuclear force, and as well as electromagnetic radiation. But what we found was that these, oddly, when we observed them, they were supposed to be massless, but when we observed them, we found that these force carriers actually had mass associated with them. Now this sent all of our theories for a bit of a six, and we really couldn't figure out how it all fit together. And that's why they predicted, so Higgs and a few of his contemporary, I think it was Peter Higgs, predicted that there has to be yet another elementary particle, which came to be known as a Higgs boson, which actually gives rise to mass of the force carrier particles, the gluon, the photon, and the two bosons that you see there. And as we sort of all know, was that now about 7-8 years ago, we found experimental evidence of this Higgs boson. And so that kind of gives, completes the picture within this standard model of physics. So again, you could spend years, decades, looking at any narrow aspect of this, but I just wanted to share with you just a rough picture of where the Higgs fits in, what are the force carriers, and what are the actual most fundamental particles. So I just wanted to quickly divert for maybe 2 minutes and just have a look at the limits of our senses, because in the end, if you think about everything that we can conceive, it's driven by stimuli from our external senses. And of course, since childhood, we've been taught about the 5 senses, and those are there. But interesting enough, there's a contention that there's 4 other senses, so balance, temperature, pain, and position. But looking at the range of these, so interestingly, I found that here are the limits for a human being on vision. So you can see candlelight at about 48 kilometers, if you can imagine, 30 miles. That's the limit of human vision. Hearing, so ticking of a watch, from a distance of 20 feet, and so on and so forth. So just out of interest to give a bit of a bounding, on what our senses can tell us. But let's look at one of those. So, ability for vision. And here's the electromagnetic spectrum. And just try to give you a bit of sense of scale here. So if you look at radio waves on the largest scale, biggest wavelengths, they're about the size of buildings. Then you move to microwaves, which starts to come down to the level of butterflies, infrared, then we have our visible, and then you go down to X-rays, which are at atomic scale. And then when you get down to so-called gamma rays, they're right down at the atomic nuclei scale. So that's a sort of range of electromagnetic radiation. Here's what we see in vision out of that. And I'll get you to note that the scale across the top is a log scale. So that the colorful piece that you see sort of around the middle of this range is all that we see in the human scale. So roughly something like a little under 400 nanometers to 700 nanometers wavelength. That's it. That's all that we can perceive. So to me, I guess it really, says it's really quite humbling to note that, I guess how little we can actually know. And even in the knowable, which is knowable matter, that comprises less than 5%, we believe, of the universe, based on our best current understandings. So that's the knowable, and within the knowable, we only know a partial understanding of that. And then we have what's the remaining 95%? So we estimate 27% is dark matter. So, this is considered to be made of what we call non-baryonic particles. So we looked at the baryonic particles in the standard model a couple of slides ago. This is something different. We don't even know what it is. So the speculation of these things called axions, or what we call WIMPs, weakly interacting massive particles. And that's 27%. And then beyond that, 68% is dark energy. So I think it sort of helps, frame a little bit of our thinking around what I would call the knowable, because these are just probably well beyond anything we can know very much about. Okay, well, just to give you a bit of a sense, so as I was saying, from the cerebral, going down to the practical. So how can we actually leverage some of this deeper understanding that we have of nature and apply it to technologies which can find use in our everyday lives? So I guess if you look at it, first quantum revolution gave us an understanding of the periodic table, of chemical interactions, electronic wave function, which gave us the ability to develop a whole range of devices which we use even without thinking today. So semiconductors, onto lasers, onto GPS or MRI type of devices, which are all seamlessly integrated into our lives. Indeed, our lives are dependent to such a big extent on these. And interesting enough, if you look at the latest generation of chips that have come out from AMD, I think it's called the Zen 2 chip. It has 40 billion transistors on the single chip. And each and every one of us, in our everyday lives are carrying hundreds of millions, if not billions of transistors in our pockets, in our phones or, other electronic devices that we have. So, over the last 50 years, we've really leveraged this idea of understanding nature and exploiting effects which passively occur in nature for all of the types of applications that we've just looked at. But now, over the last couple of decades, we've started to get the ability to engineer quantum effects that don't exist in nature. And much as you can think of creating new materials which have great tensile strength, great resilience and endurance properties, similarly with quantum, we're creating effects or quantum states that just don't exist naturally. And as a result, we're now heralding a second quantum revolution. And areas where it will find application, at least the initial areas which we're seeing, is in quantum computing, So imagine being able to solve, and we'll look at this a little more detailed on the next slide, being able to solve some of the extremely difficult problems which are at the edge of our ability of computational power, even our supercomputers cannot contend with today, to quantum sensing. So if we look at surveilling our coastline, let's say the coastline around India is so large, and we want to look for submerged objects under there, submarines, for example. Quantum sensing gives us an ability to do so at a much greater degree of accuracy than what we can with today's technology. Quantum imaging. Now imagine being able to detect a cancerous cell when it's at the single cell level, so that you're able to then send in maybe a nanobot or various amazing things that are being thought of, just inject that into your bloodstream. It goes and hunts and finds that single cell and destroys it. Revolutionary. And then of course some incredible applications to communications and cybersecurity. But let's look at one of these, which is its application to computing. So there are a number of problems which rapidly get to the edge of our computational capabilities today. A very simple one, just to share with you, is modeling a molecule of coffee. That is beyond the ability of even our best supercomputer today. Imagine that, just a molecule of coffee. You can't do it. And to particularly predict how it evolves over time. So that's because if you look at the left-hand side of this graphic here, if you had a traditional computer, and let's say you wanted to do some search, which involved looking at a phone book, which had all the A's, then all the B's, and all the C's, and so on, all the way down to Z. And I had a phone number, but I didn't know whose number it was, and I wanted to find it out. So the way I would do it is I'd probably get all the A's, look for the match on the number, then go to the B's and the C's. If I want to go faster, I'd get two computers, and one would go A to L, and the other go M to Z. And if I want to go faster again, three computers. So what you see is a linear speed up as you add more and more computers. In the quantum world, it's a little different. As we saw with the superposition idea, instead of a computer, which has a bit, as you can see in the middle column of the right-hand side of your screen, it's either a 0 or 1. But in a quantum computer, it's a 0 and a 1 at the same time. So if I wanted to search zeros and ones, instead of having two cycles, like on a conventional computer, I could do it in one. So you say, well, that's not so interesting. But let's say we go up to 3 now. In three bits, I can have 8 possibilities, which are shown on your screen there. But on a quantum computer, I can have all those 8 possibilities captured in a single cycle. So you get a speed up instead of trying to go 8 times to look through 000, 001, 010, etc. I can do all of that in one cycle. Again, not terribly interesting. But the point is, once you get to larger numbers, this is scaling exponentially. Every time I add one more qubit, I'm doubling the power. So the contention is once we get to a quantum computer of about 60 or 70 qubits, it's 2 raised to the power 60 or 70, which would be more powerful than our most powerful supercomputer that exists today, just with 60 or 70 qubits. And if we had 200 qubits, the contention is that it will have computational power more than all the computers on the planet put together. So remarkable speed up. Now it's non-trivial. These qubits are very fragile, very difficult to keep them in this superposition state, and especially when you put many of them together and you entangle them, as we discussed before, very rapidly that entanglement dissipates, it collapses. So a lot of work going on to being able to capture this. And how can we use this? So if we look at different potential applications, here's just a little sampling of it. So machine learning. So when we have AI and big data, you really have such enormous volumes of information that our supercomputers struggle to process them in adequate time and indeed look for patterns and matches within those huge data sets. Optimization. So this is the so-called traveling salesperson problem, a really well-known problem in what's called complexity theory. So this is when you look at, the problem is quite simple. It's a salesman who has a number of destinations to go to and is trying to determine the most optimal path to be able to go to all those destinations in the shortest amount of travel time. Believe it or not, if you have 20 destinations, a supercomputer, best supercomputer today, cannot figure out what's the best optimal way to visit all those 20 destinations. So we approximate it. And in fact, here's an interesting fact from UPS, the package delivery company. They said that for their drivers, if they could save 1 mile, only 1 mile per day for each driver by having a optimal path for the deliveries, just save 1 mile per day, it would straight away add $50 million to their bottom line every year, just by doing that. So this is one of the things that a quantum computer could solve quite well, optimizing such paths. Simulations, as we said, coffee molecule, beyond the best capabilities of our supercomputers today. So protein folding, new drugs, all kinds of designer medicines, all of these could become possible. Financial services, so some of the world's largest banks are already experimenting with quantum computers for portfolio optimization. Or I should have said in the biomedical and pharma area, a number of the world's largest pharma companies are already starting to use quantum computers. Similarly, for portfolio optimization in the financial services and to identify global risk factors. And then, of course, in cybersecurity, a number of our encryption systems we use today will be broken once we do have a quantum computer at the right scale. And in fact, on the right-hand side here, what you see is that Sundar Pichai, the CEO of Google, with their chip, their quantum computer. It's called the Sycamore. So this, I don't know if many of you followed, I think it was September last year, achieved something called quantum supremacy. Sounds like something out of the Jason Bourne series. I think quantum scientists prefer to call it quantum advantage. They were able to demonstrate for the first time ever solving a particular problem. In this case, it was a very specific esoteric problem, which was looking at comparing two random strings and trying to determine if they were indeed distinct and identically distributed. So they suggested that, to their credit, Google said 2 years prior to showing this, if we show you that this problem can be done very fast on a quantum computer, will you accept this as a valid proof point? And people said, yes, we would. So 2 years later, as I said, about September last year, they demonstrated that this solved that particular rather esoteric problem, and it did so in 200 seconds, so just over 3 minutes. And what they suggested was that it would take IBM's best supercomputer 10,000 years to solve that same problem. IBM came back and said, no, look, you guys didn't do it right. It's much quicker than that. It'll only take 3 years. But, okay, fair enough. Well, 3 minutes versus 3 years. I think you still got a very demonstrable advantage there. And Google used 53 qubits in this particular Sycamore demonstration. So the interesting thing about it was that there was a guy called Scott Aronson, who's quite a known person in quantum physics, an eminent scientist. So he said, well, it's what the Wright flyer did, right? It was never useful as a plane, but it was designed to prove a point. And it did prove a point. I think the same thing applies to the Sycamore demonstration here. So very interesting thought. There's this guy called Roy Amara. And he's a researcher at the Stanford Research Institute. And I thought he gave a very insightful thought here, that we tend to overestimate the effect of technology in the short run and underestimate its effect in the long run. When new technologies come about, we all get so excited and tons of money is poured in, and as Gartner calls it, then the technology is not quite ready. So you fall into this, they call it the trough of disillusionment. But eventually, everybody's saying, it's never going to work, it's never going to solve any good problems or real world problems. But then the technology does mature and eventually come to real world adoption. And Gartner, the research analyst, then called that the slope of enlightenment. So this, I think, captures that idea. And Bill Gates actually put a bit more precision around this. He reckoned that we overestimated effects in the 2-year time frame and underestimated them in a decade. So perhaps that's a sort of a closing thought, a fun thought there. But in closing, I thought I'd give you three distinct perspectives. So one from a scientist, one from a literary thinker, and then, of course, one from a philosophical perspective. And Brian Greene, as you may have read, he's got a new book out, which I haven't read yet, but it looks very interesting and, as always, thought-provoking, called Until the End of Time. And somewhat a little bit gloomy almost, but the good thing is the time scale he talks about here is like, I think, of the order of 100 billion years. And considering our universe is 11.3 billion, I think we got a while to go. But what he does say is, as we trek across time, as our trek across time will make clear, life is likely transient. And all understanding that arose with the emergence will almost certainly dissolve with its conclusion. Nothing is permanent, nothing is absolute. But on a slightly more optimistic note from Eliot, right, we'll not cease from exploration, and the end of all our exploring, we'll arrive where we started, and we'll know that place for the first time. And finally, from Rumi, this perhaps comes back to what we said right at the beginning. What we are now deducing, inferring, conjecturing, theorizing from observation and experimentation, perhaps we can arrive at from deep introspection as well. So that was some thoughts to share with you. Thank you. It's been a real pleasure. As with every journey, it's always two ways, and it makes you think yourself some more as well. So it's been a real pleasure.